name is Mark, and I'll be your chem. No, that's not how I'm going to start these things. Never mind. I'll think of something better later. But anyway, so the idea behind this show, one of many on the internet public access thing that we call Google Hangouts, is I'm going to do maybe one topic a week, one for General 1 and one for General 2, that students usually tend to have problems with, or is topical for that week, because I'm assuming most folks have started school about this time. So we'll see how long it lasts. All right, maybe a week, maybe a semester, maybe more. We'll see. Awesome. And I'm going to do it through Google Hangouts and do it live because I have no production money because I work at a community college. So anyway, we're going to start with Chem 151, or General 1. It's Chem 151 where I work at. So yeah, for General 1, the thing that most students are probably finding the most challenging is unit conversions with dimensional analysis. And that's a good one to start off with because it's going to be one that you're going to use, or something you're going to use for a big chunk of the semester. Almost all the calculations you're going to do between now and probably exam 2 is going to be unit conversion from one type to another. And then after that, you'll do some little solve for X kind of algebra. But for the most part, it's going to be unit conversions. Right. So I do another video with dimensional analysis, or I've done another video with dimensional analysis already through my Gen Chem Concepts website, which I guess once the YouTube the thing gets uploaded, the YouTube thing, once this gets moved over to YouTube after the live feed, I'll link it in the annotations right here, maybe. But I have a lot of students a few weeks down the road, once we get into reaction math, they'll say, you know, I got the unit conversion stuff in chapter 1, but now that we're using it in chapter whatever, for me it's chapter 4, for you it might be chapter 3. You know, I don't get it anymore. I got it in chapter 1, but now it just doesn't click anymore now that we've done all these moles and grams and stuff. And my response is, well, maybe you didn't really get it in chapter 1. You thought you did because a lot of those conversions were one you were already kind of familiar with, you know, like grams to pounds, miles to meters and whatnot. But what I like to do to kind of emphasize the fact that the type of unit doesn't matter is I like to do what I call alien unit conversion examples, or alternate universe unit conversion examples, where I just make up the units and I just pull them out of my wherevers. And if you're watching this and you're in my class and it's right before the first quiz, I'll go ahead and warn you that the unit conversion example that's going to be on there, and there will be one on there, it'll be a made-up unit conversion problem. So you can't just pull up your whatever and have your metric conversion app do it for you. Because I suck that way. All right, so just to give you an idea what I'm talking about, let's look at this example. Let's say, oops, no, that's not it. Let's see if I can actually do this right. All right, hang on, I gotta fix something. There we go. Forgot to load something up. I can fix that in post, right? Probably not. All right, so let's say on some alternate universe, length is measured by 2 units, Jordan's and LeBron's. And let's say that in this alternate universe, 1 Jordan is equal to 5.8 LeBrons. So you have this thing, whatever it may be, in this alternate alien universe place, that is 55 Jordans long. how long would it be in these made-up units of Lebrons? So with any dimensional analysis problem, you start with the number and the unit you're given. And again, the idea behind dimensional analysis is you want to get rid of the unwanted unit by multiplying it by one or more conversion factors. So in this case, we know we want to multiply it by something, and we're given the conversion factor that 1 Jordan is 5.8 Lebrons. And remember, there's two different ways to take that conversion factor and write it as a fraction. You can either have Lebrons on top, Jordan on bottom, 5.8 Lebrons per Jordan, or if you flip it around, it's 1 Jordan per 5.8 Lebrons. So if we write it the first way, where the Lebrons are on top and the Jordans are on bottom, then that'll allow the Joe unit to cancel. And now we see, to correctly convert between one to the other, we have to multiply 55 Jordans by 5.8. And that's the nice thing about dimensional analysis, is that you don't have to memorize all these different conversion things. To go to this, you multiply by this amount, or to convert this to this, you divide by this. You just focus on the units, and the multiplication and division will take care of itself, which gets rid of a lot of the rote memorization of converting. But anyway, here we see we have to multiply 55 by 5.8, and that will give us 319 Lebrons. Although we'd really round it up to 320 because, according to our sig fig rules, 5.8 only has 2 sig figs, so we'd round to it. So let's look at another, even dumber example. Let's say on this alien planet, volume is measured in one of two ways. You can measure it in Shazbots or Podgornies. And in this alien strange place, one Shazbot is equal to 8.104 kilopodgornies. I should point out that in this alien universe, they do coincidentally use the exact same metric system we do, which is good because otherwise this thing would just be too stupid. Right now we're in silly, but that would take us into stupid. So the exact same metric system, other weird units. So let's say you have this volume of 526 podgornies, and you want to convert that to Shazbots. So again, you start with the unit you're in, the number you're given with, or you're given. And you might want to, again, we know we have to multiply it by something, and you might want to start with the conversion that we were given, kind of like we did in the previous example. But that wouldn't work because in the conversion factor, it's in units like kilopodgornies, but in the value that's given is just regular old podgornies. So one's kilo and one's just the base unit. So that wouldn't work. But again, they use the same metric system we do. So if you have a kilo of anything, you have 1,000 of that thing. If you have a kilogram, you have 1,000 grams. If you have a kilometer, you have 1,000 nometers. So if you have a kilo podgorny, you've got 1,000 podgornies. So if we use that as our conversion factor and set it up where the podgorny unit, the base unit, drops out, now we're in the unit. Now we're in units of kilopodgornies. Yes, this is as dumb as it is to say as it is to read. But anyway, it sounded so much better in my head. But now we can use the conversion factor that was given. If we plug that in, now the kilo unit drops out, and we're left with units of whatever alien guy is, Shazbots, and that's the unit we want. So we whip out our calculator, and it looks like we have to divide by 1,000, and then we divide by 8.104, and that will give us an answer of 0.649 as our answer. So there you go. There is a couple of examples of alien conversion problems. So again, the units don't matter. The idea is just, focus on whatever the unit is, whether real, imaginary, or completely stupid like that last example. Just focus on getting those unwanted units to drop out. And after you cancel out the units you don't want and you're only left with the one you do want, then you look back and see where you multiply and divide. And if you're using my textbook, cheap plug, the last problem in chapter 1 has some more of these funky little alien conversion problem kind of examples. So that's unit conversions. So moving on to the Chem 152 guys, or General 2, I keep calling it by the course name. Where I work is Chem 151 is General 1, 152 is General 2. For the 2 people that are going to watch this that don't go to Durham Tech. Probably everybody's at Durham Tech now because I didn't advertise it. All right, so moving on to Chem 152, or General 2, see I keep doing it. For the first chapter, a lot of what we talk about in that chapter, which deals with solids and liquids, gases we talked about back in General 1, has to do with these things called intermolecular forces. So I thought for the first General 2 topic, we'd go ahead and kind of cover that for a little bit. Oops. And intermolecular forces are just a fancy way to describe the attractive forces between molecules. And really, before you talk about those, it really helps to go back and remember something from General 1, which is the idea of polarity. And if you look at a molecule like hydrogen fluoride, back in General 1, we talked about this thing called electronegativity, which says that different elements want the electrons in a bond to a different degree. It has to do with, the octet rule and all this, a lot of other stuff that, we talked about toward the end of General 1. But fluorine has a higher electronegativity than hydrogen. Actually, if you remember, fluorine's got the highest electronegativity. It's a perfect 4 because electronegativity runs on a scale from 0 to 4. So that means the electrons in that bond is going to be pulled toward it. But hydrogen has a high enough electronegativity that it's not just going to completely give fluorine that electron so it can become fluoride. But fluorine is going to be strong enough to pull it a little bit to its side, if you imagine like a tug of war, and to make it partially negative instead of totally negative. And so we use a little lowercase delta freaky musical note with a negative sign to denote a partially negative charge. By that turn, that means hydrogen is going to become partially positive because it still has those electrons in that bond. It's still sharing them, but they're a little bit further away from it. Again, it didn't completely give it up to become a cation, but fluorine is a little bit stronger, pulls it away, so it becomes partially positive. So that's basically how polar molecules work, or basically molecules with positive and negative ends to them, just like a magnet. In fact, a lot of kitty magnets have a little plus and negative symbols on them as well. So if you got molecules that are bigger than just 2 atoms, if they're linear, trigonal, or tetrahedrally arranged, which means 2, 3, or 4 things around a central molecule. One way to see if it's nonpolar is if you don't see any lone pairs on the central atom, and all the outer atoms are the same, then you can safely predict that that molecule is nonpolar with a high probability of being correct. So for example, a water molecule, both atoms are the same, but it breaks rule number 1. It has actually 2 lone pairs on that central oxygen. So we would predict it to be polar. Carbon dioxide, on the other hand, doesn't have any lone pairs on the central carbon, and both outer atoms are the same type of element, oxygen, so we predict it to be nonpolar. If it's bigger than tetrahedral, then this rule doesn't work as well, so you have to look at some other stuff that that you may or may not have been taught in General 1. But for me anyway, for General 2, I don't look at molecules any bigger than tetrahedral. So again, with intermolecular forces, you have 3 main types, or at least I narrow it down to 3 main types. First off, you have what we call dipole-dipole forces, and these are the main intermolecular forces that occur between polar molecules. So you take hydrogen chloride, for example. Remember, polar molecules have oppositely charged ends, just like magnets have oppositely charged ends. And so if you take 2 magnets and you try to stick them together, just like you'd see with magnets, the 2 oppositely charged ends would come together because opposite charges attract. And if you have a bunch of these molecules around, you might have a bunch of these different types of interactions, although this isn't drawn with any kind of scale or accuracy. I just put 5 molecules together and added some dotted lines just to give you the general idea. So that's basically how all dipole forces are. It's just the same opposite charged magnetic attraction that you're probably already familiar with. But some polar molecules actually exhibit a really special type of dipole force, and it's so special we give it its own name in its own category, and we call it hydrogen bonding. And the thing that makes it so special is that it seems to be stronger than the other regular types of dipole forces. So the way you spot a molecule that's going to exhibit hydrogen bonding is, as you'd expect, it has something to do with hydrogen. But usually it's a hydrogen bonded to a nitrogen, oxygen, or fluorine. And that hydrogen will interact with the nitrogen, oxygen, or fluorine of another molecule. So in the case of water, for example, it's the same opposite kind of attraction we saw before, but again, these attractions seem to be significantly stronger than the regular dipole-dipole forces that we saw with our hydrogen chloride example. And if we substituted fluorine for chlorine, if we made this whole thing, a bunch of hydrogen fluoride molecules, it'd be the exact same type of attraction, except these attractions would be seen to be significantly stronger. And again, they're so much stronger that they were just given its own special category. And later on, when we talk about things like boiling points and other things that are affected by intermolecular forces, you'll see why they were hydrogen bonded molecules get their own special category. But just because a molecule has hydrogen in it and an oxygen in it doesn't mean it's hydrogen bonding. It's got to be a hydrogen bonded to an oxygen. So if you look at the 2 main isomers of C2H6O, one of them, a dimethyl ether, would look something like that. And so that you have oxygen, you have 6 hydrogens, but none of those hydrogens are actually bonded to that oxygen. So this wouldn't be an example of hydrogen bonding. This would just be a regular old dipole or dipole-dipole forces between those ether molecules. On the other hand, if they were arranged to give us ethyl alcohol or ethanol, or drinking alcohol, as we call it, now you have a hydrogen bonded to an oxygen. So yeah, that should exhibit hydrogen bonding. So again, it's not the presence of hydrogen in an NO or F. It's got to be a hydrogen bonded to a nitrogen, oxygen, or fluorine for it to qualify for hydrogen bonding. So those are the two main types that you see for polar molecules. For nonpolar molecules, its primary intermolecular force is either called dispersion forces or London forces, or sometimes they're lumped together and called London dispersion forces. I tend to call them dispersion forces most of the time. But those are the main intermolecular, that's the main intermolecular force for nonpolar molecules. And a dispersion force is basically an attractive force between temporary dipoles that occur between molecules, which actually I didn't define dipoles here. Dipole is just a name for the magnetic force between the two ends of a polar molecule. So you're basically forming these temporary dipole interactions, or these temporary dipole moments. And there are two main ways that these can occur. They can occur by what we call an instantaneous dipole or through an induced dipole. And both types of dipoles are pretty much work exactly the way you'd get from the name. An instantaneous dipole happens just instantaneously all by itself. So if you imagine the electrons spinning or moving all over that molecule, if it's a nonpolar molecule, they're usually distributed symmetrically around a molecule. And the most common way to kind of show the symmetry is with a sphere or a circle, although it doesn't have to be a spherical molecule, just anything where they're evenly distributed. But as they're swirling around that molecule, every now and then you might have some electrons that some of the electrons are for a little bit more on one side than the other. So you get this temporary moment where you have more electrons on one side of the molecule, fewer on the other. That'll cause a temporary dipole to occur. But after a second, it'll go back to being symmetrical because it remembers that it's nonpolar, if molecules actually had memories. So that's an instantaneous dipole. It's just these brief little moments where these nonpolar molecules just momentarily become polar. You can also have an induced dipole, which again is pretty much the way the name sounds. It's a dipole that is caused by another molecule. It's induced somehow. And this can happen by, say, an ion coming in contact, an actual charged atom coming near this nonpolar molecule, like if a sodium atom came near a nonpolar molecule. Opposite charges attract, so the electrons would be pulled toward the end facing the sodium ion. So you get this temporary dipole that occurs, and it is temporary because once these two things move away from each other, it would go back to being nonpolar and symmetrical. But so this induction can happen from an ion. It can happen by a nonpolar molecule, or a polar molecule coming close enough to cause this induced dipole. Or you might have two nonpolar molecules close enough to each other, and one of them suddenly becomes induced, instantaneous dipole, and that instantaneous dipole can induce a nearby's electron cloud to be polar. So you can imagine all these different nonpolar molecules going around, and they're just all these brief instances of different nonpolar molecules suddenly becoming instantaneous dipoles, suddenly becoming polar, and those will induce other polar molecules. So these things will happen like all the time. On average, they're still polar, but you do get these brief instances where they are. And when you get enough of them, that can cause some of the effects that you see later on when we look at boiling point, viscosity, and all this other stuff. So if you're a fan of flowcharts, and this may not be a perfect flowchart if you're a flowchart nerd. Sorry, I just kind of put this slide together in about a minute or two. To figure out what type of intermolecular force it is, you see whether it's polar or nonpolar. If it's polar, then it can be dipole or hydrogen bonding. If it's nonpolar, it can be dispersion or London dispersion. And if it's nonpolar, you're pretty much done. If it's polar, then you see whether or not you have a hydrogen bonded to a nitrogen, oxygen, or fluorine. If you do, then the main intermolecular force is going to be hydrogen bonding. Otherwise, it's going to be dipole forces. Although for hydrogen bonding, you really don't have to go through all of this, because if you go back to the ethanol example, if you just see a hydrogen-oxygen bond or a hydrogen-nitrogen bond or a hydrogen-fluorine bond, that's just your clue right away that it's most likely going to be hydrogen bonding as its main intermolecular force. And you'll notice during the talk that I kept saying, primary or main intermolecular force. That's because dispersion forces actually exist in all molecules. It's just for nonpolar molecules, it's the main one. Now, they also exist in polar molecules. It's just in a polar molecule, dispersion forces are present, but the main force is either dipole forces or hydrogen bonding, one of those two. And that's something we talk about a little bit later in the chapter. All right. But for now, my clock, that's about 30 minutes. That's about what I was hoping to do for the first episode. So, so next week we'll talk about something, because I haven't planned anything yet. Actually, I kind of have an idea for 151 or General 1. I gotta stop saying 151 in case people actually start watching this that aren't in my class. Although I guess if you're in North Carolina and you're at a community college, it's all 151. But I think I know what we're going to talk about for General 1 next time. General 2, I got to remember what we're going to talk about next week in class. But for now, what I'll probably do with the YouTube version is have some annotations pop up here and there. So I need some time to do that. So I think what I'm going to do is I'm just going to leave you by staring at the camera, job style.